Hi everyone, once again I welcome you all in this wonderful lecture of the chapter Solid State. I'm just going to discuss about the closed packed structure in this particular lecture. In the previous part of the chapter we discussed about the different type of solids, the crystalline solid and the amorphous solid, and in the previous lecture we discussed about the crystal lattice. And now it's the turn to understand the packing of the particles in the crystalline solid. Simply, if we talk about a particular solid, particles are closely packed, we all know that, and there is very less vacant space as compared to liquid and the gaseous state. Let us begin this lecture with the discussion of closed packed structure, and we'll discuss here how this closed packing occurs in 1 dimension, 2 dimension and 3 dimension. So let's begin with the very first point, that's closed packed structure. What do you know about it? If we talk about this closed packed structure, we can say that in case of solids, the constituent particles are close packed in such a manner that they leave the minimum vacant space. Basically, if we talk about solids, these are rigid. They have very less interparticle space. We already discussed in the previous classes. So, what is new here? In this part, we are just going to discuss that consideration that leaving least vacant space, how does affect the stability of the solid. So simply one thing you should know, that closed packed result in minimum vacant space, and if minimum vacant space is there, it means more stability is there. So simply we can say closer the particles in case of solid, more would be the stability of that particular solid. Again the point to remember that close the particles, more stability. Now when I say particles are closely packed, now how these are packed? It is the point of discussion. How would we know that particles are closely packed? The first important thing, what are particles? Particles can be ion, can be atoms, can be molecule also in case of solids. And these are that attached to each other that they are leaving minimum space. So first thing that we are going to discuss here is a closed packing in 1 dimension. Very much important thing is there. What is the shape of the particle? Particle can have any of the shape, but in this part we'll assume that particles are spherical, because we know that in case of sphere the surface area is minimum and they can be closely packed, and we'll assume here that these are closely packed in such a manner that they are leaving minimum vacant space, the point to remember here. And if we talk about the closed packed structure in 1 dimension, we assume that particles are present in the form of ball and they are arranged in a row. Suppose I have a single ball. That ball is joined with other ball, with third ball, with fourth ball, and ultimately there is the formation of row, and that is termed as 1 dimensional closed packing. Now again the question arises, if you look at this ball, suppose I am talking about the single ball and this is directly attached with 2 balls. It means these are the 2 nearest neighbors of this ball, and on the basis of the number of nearest neighbor, we use a term coordination number. Coordination number represent the nearest neighbors of a particular particle present in the solid state. So simply we can say that the number of nearest neighbors of a particle is called its coordination number, and each sphere is in contact with the 2 of its neighbors. In case of 1 dimensional closed packing, there is each sphere that is in contact with 2 of its neighbor. So what would be the coordination number? Definitely it would be 2. So I'm just writing here the coordination number in this case is 2, because particles are directly attached with 2 more particles. Now here I want to show you the closed packing in 2 dimension. What does it mean? It means that in this part we are talking about the plane. In the previous part we were joining the balls in the row, and here there is the formation of a plane. It means 2 dimensional discussion would be there. How this plane can be formed? Suppose you have a single row. Let's assume that row is A row. Let's take another row and just place that row below that row, and after that place the third row, then the fourth row, and on the basis of this you can form a plane. It means there is the formation of a layer, and this layer represents 2 dimensional closed packing. Now again question arises, two-dimensional close packing can be done in how many manners? If we talk about the close packing in two dimension, there are two possibilities. One, just take a row and place the particles over the particles of the other row. Similarly, one more thing you can do here, that you can place the particles of the second row in the depressions of the first row. You can clearly look at here that depressions of the first row are clearly visible, and over those depressions you are placing the particles of the second row. This is another possibility. It means in case of close packing in two dimensions, there are two possibilities. So here we can say that two-dimensional close packed structure can be generated by placing the rows of close packed spheres over one another. I have already told you this fact, and on the basis of this there can be two types of close packing in two dimension. One is the square close packing in two dimension and other is the hexagonal close packing in two dimension. So first is the term for square close packing in two dimensions. In this case, the second row may be placed in contact with the first one in such a manner that the spheres of the second row are exactly above those of the first row. How it can be done? I am just going to show you the diagrammatic representation. You can clearly see here that first row is there. Let's assume that row is row A. Let's take another row and place that row on the first row in such a manner that particles of both these rows are in close contact. After placing that, you will see that both the rows are exactly same. So suppose first row is row A, the second row is also termed as A. Place the third row in the similar manner. What is there? There is again another A row. It means this type of formation of layer can be termed as A type of arrangement. Why? Because these three rows are exactly similar. Let's place the fourth row also. We have this layer that's formed here, and this is close packing in two dimension. And what is the special name given to such type of close packing? That is square close packing in two dimension. And this type of arrangement is known as AA type of square close packing in two dimensions. Now again, I just want to ask a question. Suppose I am talking about a single sphere which is present here. Say that particle is given here, and you just identify how many particles are there in direct contact with it. Just identify. Yes, these are 4 particles which are in direct contact with this sphere. It means nearest neighbors 4, coordination number also 4. So you can easily identify the coordination number in case of square close packing, that is 4. After this, here is a hexagonal close packing in two dimension. We already discussed that if you place the second row in the depressions of the first row, then you will obtain another type of close packing in two dimension, and that is termed as hexagonal close packing in two dimensions. So here you can define it as the second row may be placed above the first row in staggered manner so that its spheres fit in the depressions of the first row. Again, you want to see the diagrammatic representation, I know that, so I have this for you. The layer A is here. This is the row A, and above it I am just going to place the second row. Let's take the second row here and place that in the depressions of the first row. I have placed that. You can clearly see that in this case row A and row B are different. Let's place the third row in the depressions of the second row. If you place that, you will see that first row and third row are exactly similar. Now place the fourth row also. After placing the fourth row, you will identify that second row and fourth row are exactly same. It means if first row is row A, then definitely third row is also row A. While if we talk about the second row, if that is row B, then fourth row is also row B, and this type of arrangement is termed as AB type of arrangement. Why AB? Because first and third layers are similar and the second layer and the fourth layer is similar. Now again, in this case you have to identify the coordination number. It's your turn. Suppose I have the sphere here. Just identify the nearest neighbor of this sphere. Identify. You will see that it is in direct contact with 6 spheres. And if it is so, it means 6 nearest neighbors are there, and that's why the coordination number in this case is 6. So never be confused. If we talk about the square close packing, the coordination number is 4. We are talking about the 2 dimensions only. And in case of 2-dimension hexagonal close packing, then definitely the coordination number is 6. Now after this, we can say that when the third row is placed over the second in staggered manner, its spheres are aligned with those of the first layer. I have already told you. And second point, the spheres of the fourth row placed in similar manner will be aligned with those of the second row. These points I have already told you. I hope the square close packing in 2 dimension and hexagonal close packing in 2 dimension is clear to you. And till now we have discussed about the close packing in 2 dimension. So what is the next point? The next point is close packing in 3 dimension. So let us move towards that part.